Okay, we're going to approach the power rule with this little discussion today, and then we'll also talk about differentiation as a linear operator. Okay. The power rule says that if y is equal to x raised to some number, then y prime equals that number times x raised to the number reduced by 1. So there's a statement of the power rule. Let's use it in an example to demonstrate how it's used. Here it is written again. We have the power rule right here, that the derivative of x to the n is equal to n times x to the n minus 1. So now let's suppose we have the function f of x is equal to 1 over x squared, and we want to find the derivative of that function. Okay, well, if that's our goal, what we want to do is apply the power rule. Now, if we have this as a fraction, we could rewrite f of x so that it's x to the negative 2, because of course that negative exponent indicates that the base is actually in the denominator. And now we'll apply the power rule. We'll find f prime, the derivative, using the power rule. Now the power rule says that the exponent comes out here and becomes a factor times the x. So, and then we subtract 1. So that's what we're going to do. We'll take the negative 2, put it out front, write down the x, and subtract 1. Negative 2 minus 1 is negative 3. And so the derivative is negative 2 times x to the negative 3, which is the same thing as negative 2 times 1 over x cubed, or just more simply, probably negative 2 over x cubed. Okay, that's an application of the power rule. Let's now talk about the fact that differentiation is a linear operation. If an operation is linear, then it has a certain characteristic. For differentiation, here's the operation symbol for differentiation, d over dx. Let's say we were trying to differentiate the function f plus k times g, where k is a constant and f and g are differentiable functions. Okay? Then, since differentiation is a linear operator, this will equal the differentiation of f plus k times the differentiation of g. Okay, let's apply that to an example. Let's suppose we had the function f of x, or let's just find the derivative of a function. Let's say our function was 5x cubed plus 3x squared over x. The first thing we might do is simplify this argument. We might recognize that that argument there, that function, that rational function, simplifies to, if we think of the 5x cubed over the x plus the 3x squared over the x. In other words, we decompose the fraction. We see there's a common denominator. We just add it up and be back to where we were before. Now, continuing with that simplification, we'll reduce those fractions, and we have 5x squared plus 3x. Now, since differentiation is linear, I can bust this up into two operations, and I can say that this is equal to the derivative of 5x squared plus the differentiation of 3x. And I can also take these constants and kick them out and make them factors. So there'll be 5 times dx of x squared plus 3 times the differentiation of just x. Now, we recognize this derivative as 2x using the power rule. So this is 2x, so it's being multiplied by 5. And then this derivative is just 1, being multiplied by 3. And so we see that the derivative was 10x plus 3. And that was the derivative of 5x cubed plus 3x squared all over x. Now, you may not show as many steps in your work as we did here, because you may quickly, when you're differentiating this, just say, well, 2 times 5 is 10, and back that off 1 and get your 10x, and 1 times 3 is 3, and back that off 1 to 0, so that there is no x, so we have 10x plus 3. That's what you'll be doing throughout the semester, but the reason why you can do that, you can bust it up in this manner, is because differentiation is a linear operation.